Let ABC have side lengths 30, 32, and 34. Point X lies in the interior of BC, and points I1 and I2 are the incenters of ABX and ACX respectively. Find the minimum possible area of triangle AI1I2 as X varies along side BC. This is triangle ABC, which has side lengths 30, 32, and 34. Point X lies somewhere on BC, and we have the incenters I1 and I2 of triangles ABX and ACX. We want to find the minimum possible area of triangle AI1I2 as X moves between the points B and C. We start by finding a way to generally express the area of triangle AI1I2. The area of triangle AI1I2 is equal to AI1 times AI2 times 1/2 the sine of the angle I1 AI2. We first have to find AI1 and AI2 using the law of sines. By the law of sines, AI1 using triangle AI1B, AI1 over 30 is equal to the sine of the angle opposite AI1, which is ABI1, over the sine of the angle opposite AB, which is 30. That's the angle AI1B. The incenter is the intersection of the angle bisectors of a triangle. So we can use this, and we find that AI1 equals 30 sine angle ABI1, which is just half angle B. I'll write B over 2 over sine angle AI1B, which is well known to be just 90 plus 1/2 angle AXB, which from now on we will refer to as alpha. Similar computations to the one I did just now, we can get AI2 equals this expression below AI1. We can simplify the two expressions we got for AI1 and AI2. For AI1, the sine of 90 plus alpha over 2 is just equal to the cosine of alpha over 2. And for AI2, the sine of 90 plus 180 minus alpha over 2 is just the sine of 180 minus alpha over 2, and that's just the sine of alpha over 2. We can form these expressions for AI1 and AI2. The last part of this area formula for triangle AI1I2 is 1/2 sine angle I1AI2. Because the incenter of a triangle is just the intersection of its angle bisectors, as I said earlier, the angle I1AI2 is simply BAX over 2. That's the left part of this angle I1AX. The right part of the angle, which is I2AX, is just angle CAX over 2. When you add these, it gives you just angle A over 2. By now, this information has helped us figure out a new formula for the area of triangle AI1I2 that's given by this stuff over here. Note that the denominator of this fraction, 2 cosine alpha over 2 sine alpha over 2, is simply equal to sine of 2 times alpha over 2. So we can make it even simpler by writing this. If we want to minimize this fraction, which is what the area of AI1I2 is given by, we need to maximize the value of sine alpha. That can only be done when alpha is equal to 90 degrees. So in short, the largest possible value of the area of AI1I2 will occur when alpha is equal to 90 degrees, or AX is an altitude of triangle ABC. This is much easier now because sine alpha is equal to 1. Therefore, we just need to calculate the value of this expression. We can find the values of sine A over 2, sine B over 2, and sine C over 2 by using the incenter I of triangle ABC and projecting it onto the three different sides. If the in radius of triangle ABC, that is the radius of the in circle of triangle ABC, is denoted as R, then we get sine A equals R over AI. sine B equals R over BI, and so on. So we can write the area of triangle ABC as 30 times 34 times R cubed over AI times BI times CI. It's known that AI times BI times CI is equal to 4 times big R times little r squared. So we can write 30 times 34 times R cubed over 4 times big R times little r squared. That's just 30 times 34 times little r over 4 big R. This can be simplified into 255 little r over big R, where little r denotes the in radius of ABC and big R denotes the circumradius. Using well-known formulas, little r is equal to the area of triangle ABC over its semiperimeter, and big R is equal to the product of the side length of ABC divided by 4 times triangle ABC's area. So first, let's find little r. By Heron's formula, the area is equal to triangle ABC's semiperimeter. That's 30 plus 32 plus 34 over 2. That's 48 times 48 minus 30 is 18. 48 minus 32 is 16. And 48 minus 34 is 14. And we have to divide all that by the semiperimeter of triangle ABC, which is 48. And this turns out to be 96 root 21 over 48, which is just 2 root 21. And now big R is going to be easy to find because we know the triangle ABC has area 96 root 21. So we can do the product of the side lengths of ABC is 30 times 32 times 34. And then dividing that by 4 times the area of ABC, which is 384 root 21. We're going to get 30 times 34 times 1 over 12 root 21. 32 over 384 is 1 over 12. And that turns out to be 85 over root 21. So now we know that R is equal to 2 root 21 and big R is equal to 85 over the square root of 21. We want to find 255 little r over big R. So that's just 255 times 2 root 21 times root 21 over 85. Root 21 times root 21 is 21. So we just have 255 over 85 times 2 times 21. 255 over 85 is 3. So we really just have 3 times 2 times 21. And that's equal to 126. Thank you for watching, and please subscribe to my channel if you would like to see more videos.